Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, of course, we were talking about some of the models, let's say, for the atom, and of course some of the scientists, which of course they're proposed or what they have proposed regarding the atom. Making it short, this is where we stopped last time. Basically, we went through this one, but I wanted to start from this one more time, and then after that, continue from this. So consider this let's say, a short review. Okay, so last time we were saying Rutherford proposed a planetary model of the atom. And of course, we said that, or the concept of this one, Rutherford proposed that electrons orbit, let's say, the nucleus, just like planets orbit the sun. So basically, they orbit nucleus in a, let's say, in circle, let's say, revolving around or orbiting around the nucleus. That's one of the things that he said. But of course, like how did it all start, you can say? The Geiger-Marsden experiment, they basically did an experiment like the Geiger and the Marsden experiment. So they did an experiment. That experiment, of course, to challenge and test the validity of Thomson's model or atomic model. If you remember, Thomson said that atoms, of course, it looks like, let's say, if we make a short, of course, we'll say more like a watermelon, yeah? That'll be all positive, let's say composed of positive charge with electrons embedded into that. Or you can say electrons would be resembling the watermelon seeds inside the watermelon. That basically what Thomson did. So of course, to test the validity of that model, they did an experiment. Yeah, that was basically, you can say, Geiger and Marsden experiment. So the challenge was, or you can say, to challenge and test the validity of Thomson's model. What did they do? Hans Geiger and Ernest Marsden, under the supervision, of course, of Rutherford's, they projected a beam of alpha particle. Remember, when we say, or you can say positive charge, which was an alpha particle. Alpha particles normally have two protons and two neutrons, you can say, at a thin metal foil. Okay, so you can say a gold foil, to be more precise. So what did they observe here? Like, to make it short, they saw that the majority of these alpha particles went right through the atom. And of course, it was a bit surprising for them because based on Thomson's model, all these particles were not supposed to pass through because remember, it was, or the nucleus was, let's say the atom was supposed to be all positive charge with, let's say, electron or negative charges being, let's say, embedded through them. That's this. But that's not what they have discovered as a result of the experiment. Yeah? They saw that most of alpha particles went right through, okay, except then for, you can say, there were some unexpected deflections. So what were these deflections? They saw that some of these alpha particles were, let's say, deflected at some angle, and of course some other particles, let's say, went right, let's say, back at a, let's say, if we become more precise, we'll say 180 degrees. So let me tell you exactly regarding this experiment, or how can we let's say, demonstrate this experiment here. So let's say this is the alpha particle that, let's say, they descend through the atom here. So if we assume that this is the atom here, they saw that most of these alpha particles were right, or went right through this one here. Okay, that is most of them. But except then for some of these alpha particles, we can say, let's say some of these alpha particles were shifted, you can say. That is because, remember, alpha particles are positive. So positive and positive, it would shift, it would kind of push away or move away from one another. And we can say for some of other, let's say, particles here, we can say this alpha particle at some place here, you can say this has went right through here. So you can see that this is an alpha particle that went back through at, let's say, 180 degrees here. And of course, you might say, but how did they do that? And of course, there was a detector. These detectors were kept moving, for example, to detect how many alpha particles are moving or passing through. And of course, regarding this one as well, so detecting all these alpha particles. So that was the result of the experiment, noticing that, or knowing that most of the alpha particles went right through. Some of them were deflected at some angles. And of course, you can say very few were deflected at a great angle, or you can say 180 degrees here. Okay, so that was the unexpected deflection, you can say. So what was Rutherford's reaction and conclusion for this, for the experimental, or for the result of this experiment? You can say that Rutherford was very astonished, and of course he describes the experiment as incredible. He also said that this experiment is like firing a 15-inch shell at a tissue paper and having it bounce back. What does it mean? Imagine if you, for example, firing a bullet into a piece of tissue, and then this bullet, or the tissue, being able, or to make the the bullet bounce back or go back. Yeah, that's exactly how it was for, let's say, the Rutherford force. So what is the conclusion, or what do we get as a result of this experiment? One thing, we can say that atom is positive charge and most of it is masses, by the way. And regarding this one here, I forgot to tell you this. And of course, we can say that, let's see, not this one here. We can say regarding this one, okay, remember, this, not only the nucleus of this one, this part, or you can call it nucleus, must be very dense. What would have happened if it was not very dense? Of course, you could have noticed that, let's say, these alpha particles would have been able, let's say, to shift the nucleus from this place. But if something, imagine if something is very dense and heavy, of course, no matter what you're firing at, it doesn't move. Let me give you an example. Let's say that you have a box, which is basically metal, it's very heavy. And what happens when you fire some bullets at that big box of metal, let's say, or big metal, yeah, box? In that case, will it move? Clearly not. Why? Because the metal box would be way heavier than the bullet, even though the bullet could be very strong once it is being fired to the box. But what if it was something, for example, let's say as small as a small box, let's say, yeah? In that case, of course, the bullet would have been able at least to slide or move, let's say, the box out of place, let's say, because in that case, we can say the box is not that heavy. It can just move or shift, let's say, the box on the way. But that was not the case. So based on this, we can say the nucleus must be very dense, or you can say all the mass of the atom, it is concentrated at this nucleus right here. Okay. So one more time, we can say most of the atoms positive charge, most of the atoms positive charge, and most of its mass are concentrated in a very small region. And that region, of course, is called the nucleus. Now, next thing we can say electrons occupy. By the way, if we go back to the other one here, we can say that electrons occupy a very large volume here. So, of course, we can say if this is the nucleus, where do you think the electrons are? Of course, they must be occupying these spaces, which this space, of course, even if we consider this space to this one, which are not, let's say, to scale, because the size of the nucleus will be way smaller compared to the size of this circle that I've drawn here, like this two, you can say most of this, or most of the atom's size, you can say, or most of the atom, of course, it is empty space in that case. Sorry. The alpha particles that were deflected or bounced back, of course, were those that passed close to very close to the dense nucleus, while most particles pass through the empty space here. Now, what was the impact of this, let's say, what was the impact of this result on the atomic theory? Of course, this experiment demonstrated that Thomson's model within its evenly distributed positive charge could not explain, of course, the large, let's say, angle deflection. They couldn't do that. And then we can also say that Rutherford's model introduced the concept of the nucleus, which is basically fundamentally altering the understanding of atomic structure, you can say. So this basically, you can say, the nature of the experiment. This is alpha particle, directing alpha particle to a metal foil. You can say gold foil here. And of course, these are the viewing screen, you could say. So what happens exactly? If we, for example, go back to this one, you can see that most of these alpha particles went right through here. For some of them, they deflected at some angles. And of course, you can say other few particles were bounced at, let's say, 180 degrees there. Okay, so we can say majority of alpha particle went through. This is the atom of gold foil. We can say majority of alpha particle is the same. And of course, few of them were bounced back or deflected. Okay, now based on this, of course, we can explain this a bit more here. So we'll say Rutherford's model, an unstable atom, yeah? This model, or the Rutherford's model, of course, was not very complete. It has a flaw, it has a defect, yeah? It was not complete. So we can say Rutherford's experiment, like what did he, what was the experiment? He suggested that the electrons orbit the nucleus just like planets around the sun, for example. They're just like nucleus, or just like planets orbit the sun, for example, which explains why they aren't pulled into the nucleus. So planet, or you can say electrons, if this is the nucleus, for example, electrons would orbit this nucleus just like planets, for example, orbit the sun here. That is the first thing you can say. And of course, if we demonstrate that or using a diagram, this could be very close to one. So in Rutherford's model of the atom, electrons orbit the nucleus in a manner, you can say, which is similar to the planets orbiting the sun here. But there was a problem with the model here. So what was the problem with the model? Now, before that, or you can say, according to Maxwell's theory, orbiting electrons should radiate electromagnetic radiations as they orbit the nucleus, yeah? So if that is the case, then they must, for example, spiral into, for example, if starting with the electron here, so Rutherford said these electrons orbit the nucleus just like planets orbit the sun, yeah? But then, based on Maxwell's, you can say, theory, if electrons are orbiting the nucleus, then they must give out or radiate electromagnetic wave. And if they radiate electromagnetic wave, that means they are getting closer, or you can say there is a centripetal force here. So they're getting closer and closer to the nucleus here. So if we draw this one here, if we make it more precise, we can say they must get closer and closer, let's say, to the nucleus, yeah? And once this happens, of course, what do you think will happen? What do you think will this be the effect, or this effect will be on the atom? Of course, this would lead to the collapse of the atom, okay? So once again, this was a defect. Rutherford could not explain this one, or he could not, or he did not have an explanation for this. According to, or based on Maxwell's theory, if electrons orbit the planet, orbit the nucleus, then they must give out electromagnetic radiation. And of course, there is centripetal force, you can say. So they give out electromagnetic radiation, and of course, once they do, they get closer and closer and closer to the nucleus until they fall, or you can say into the nucleus. And of course, this is the correct term that we use. We say it spirals into the nucleus here. And if this happened, that means the atom would collapse here. Okay, so that was one of the effects here. And of course, you can say this energy loss would cause the electrons to spiral into the nucleus, leading a collapse of the atom. Imagine, so if that was true, then calculations indicate that the atom would collapse in 1 billionth, remember, all right? So we have 1 million, that will be 10 to the power 6. 1 billion, that is 10 to the power 9 here. So the atom would collapse in a time, you can say, in a time of 1 over billionth, you can say, yeah? So if I write this one in number, it would say that the atom would collapse in a time of 1 billionth. So this is 1,000, this is million, and this is, you can say, billion here. I think, yes. So this would be for that. If not, you could just write this one in power, which is 10 to the power 9 here. So this is how long it takes an atom to completely collapse, if that was true here. Okay, so this was the, you can say, that would be the conclusion here. So, and of course, you can say that highlighting a major flaw in Rutherford's model, and of course, promoting the search for a new model, because if this model has a flaw, then of course you need to look for a better explanation or a new model. Now we have a question here, says, what did Rutherford's foil experiment reveal? Okay, and of course, it revealed that based on, for example, what did it reveal? It revealed that you can say that the positive charges, and of course, and most of it is, or most of the atom's mass are concentrated, you can say, in a small region, that small region that is called the nucleus. What about the surrounding? And of course, it must be mostly empty space. That is where the electrons, you can say, orbit there. Now we have another question, says, if Rutherford's planetary model were correct, atoms would be extremely unstable. Why? Because we said it, yeah? Based on Maxwell's theory, if electrons are orbiting the nucleus, then they should radiate electromagnetic wave. Then their energy, of course, becomes less. In that case, they have centripetal force or centripetal acceleration. They get closer and closer to the nucleus until they fall, collapse into the nucleus, and that would lead to the collapse of the atom. Yeah. So of course, you can say electrons radiate energy. The orbit radius would decrease, causing increasing radiation, and of course, a rapid collapse of the atom as electrons spiral into the nucleus. All right, now let's talk about two more things here, you can say. What about atomic spectra here? Now, scientists aim to develop new atomic model. Scientists try to, let's say, have new atomic model for two reasons, you can say. One of the reasons is to solve problems with Rutherford's model, because we said that there was a problem, yeah? And that problem, of course, electrons, once they move in an orbit around the nucleus, they spiral out, and then that leads to a collapse of the atom, okay? So to solve this issue, and then another issue was, or you can say to explain the behavior of gas, because gases, right, can behave, let's say, under certain circumstances, they behave in a way that, let's say, classical physics or some scientists could not explain by that time. Okay, so let's talk about each one of them first. So solving problem with Rutherford's model, and of course, because that problem should, let's say, address issues with Rutherford's planetary model, that's 1 second, explain or to be able to explain the gas behavior. What do we mean by gas behavior? And that we mean basically, like these behaviors. What exactly are those behaviors? We'll say when an evacuated glass tube, for example, let's say that if we bring a glass tube, all right, so let me do this one a little bit here. When we, for example, bring a glass tube, if these glass tubes, let's say, are filled, let's say, first of all, evacuated here, and then after that, let's say, we put a gas, let's say pure atomic gas, let's say, and of course, let's say, so there is a gas in here, yeah, and then after that, we're going to apply, let's say, a certain potential, let's say, a voltage or potential difference across the edges of these two. So let's say one side is positive, the other side negative. Then of course we get, let's say, this gas in here, it starts to glow light, let's say. And if we examine this light, let's say, using diffraction gratings, let's say these are some diffraction gratings, and then later on a prism here, and a screen as well, we would see that these gases, of course, will emit, let's say, certain, let's say, or give out certain colors of light, okay? And this, of course, these colors of light are called emission spectrum, or let's say, emission spectrum, that basically the gases, or let's say the light that we get from these glowing gases. So I'll repeat this one here, yeah? Because, and by the way, if this is one gas, we'll get one type of spectrum. If we try another gas, we'll get a different type of spectrum, yeah? And of course, these are, you can say, bright lines here. And of course, this comes from this gas right here. So once again, like what is the procedure here? We have an empty glass tube. And if we, for example, add some gases, or you can say pure atomic gases, okay? So in that case, if we add this gas into the glass and then we add a potential difference to the two ends of the glass, we'll see that this gas, all right, clearly there will be electrical current through this one. While electrical current passes through this one, this gas glows light. And of course, if we examine this light using diffraction grating, and then after that put this light onto a prism, we'll see that it produces, and if this is a screen, we'll get a spectrum here, or you can say some visible colored light here, okay? These colored light here is called spectrum. And of course, the spectrum of one gas that is different from the spectrum of another gas. Once again, we needed a model to explain this because so far all the, let's say, methods or theories that we had about the atom, they could not explain this behavior. That, of course, you can call the gas behavior. Okay, so one more time, gas behavior. An evacuated glass tube filled with a pure atomic gas has a significantly high potential difference. If, of course, we add a very high potential difference to the two ends of the metal, or metal electrodes, you can say, it produces a current in the gas. This current causes the tube to give off light, to glow light. And of course, with the colors of light being characteristic of that gas. So we can say every gas would have a different color. So you can see here, for example, now we have one of them is mercury. The other one is, of course, the hydrogen, mercury, and of course, we have nitrogen. Each one of these, of course, would give out different colors here. So one example for that, gas is giving out light, that would be the neon signs operate on this principle. Sometimes we do have like these glasses or these lights, for example, it is neon. It contains a gas that is neon, basically. So when there is a potential difference applied to the edges or to the ends of these glass tube, it produces or glows light. Yeah, that is one example. One of the examples of that would be. So with a variety, with a different of colors or different of colors seen resulting from different gases in the tube here. So these would be some of them, and of course this would be the procedure that we have here. So we can say each gas has a unique emission and absorption spectrum. So what do we mean by this? Now, there are two types of spectrum here. We have emission spectrum and we have absorption spectrum. I hope the name, clarifies the situation here. One of them, let's say the gases can give out the light, just like we said, for example, we have a gas, put it into a, let's say pure gas, put it into a certain glass, apply high voltage across the two ends, let's say, and then that light, of course, will be able to conduct electrical current, and then the gas glows off. So the light that we get from this phenomena, you can call it emission spectrum. Why? Because it emits, gives off light. But then we can also do something else here. For example, yeah, so let's say we have a certain light. If we allow this light to pass through a certain gas, remember this, yeah, then this gas will be able to pick up, right, or to observe, to absorb, let's say, a part of or specific, some certain wavelength of that light, and then after the light passes through the vapor of that gas, and if we use, let's say, diffraction grating a prism on a screen, let's say, we'll see that. And if we, for example, if we examine that light, we'll see that some of the lines are missing, or you can say there are some dark lines on the spectrum of the light that is, let's say, falling on the screen. And that is called absorption spectrum. What exactly means absorption spectrum? That means some of the wavelength that is inside that light, it is absorbed by the vapor or by that gas. Now, of course, we don't see them on the screen here. And by the way, once you compare the two, if it is the same material, or you can say the same gas, you will see that the absorption spectrum and the emission spectrum would match. Why? Because it is the same wavelength that has either been, let's say, emitted or absorbed here, which indicates that, for example, if it takes, let's say, let's start with this one. For example, if it takes 10, let's say, not 10 electron volt, let's just use like just numbers for the sake of the example. If an electron needs 10 joule, for example, to move to a higher state, an excited state, that means it can absorb 10 joules of, let's say, energy. But then as they fall back or go back to the same energy level, they radiate 10 joules. So you can see that the same amount of energy, let's say, that is absorbed will be given away when it is going to, let's say, a lower energy state here. So that is why emission spectrum and absorption spectrum would be, you can say, unique. But one of them with a visible light spectrum, the other one with, you can say, dark lines, representing the same wavelength of light being absorbed or emitted here. So one more time, let's go through the details. When a light is given off or emitted by an atomic gas, is passed through, watch this, it passed through the prism, as shown here, let's say a series of distinctive bright lines is seen. So this is what we're talking about here. Yeah? Each line corresponds to what? A different wavelength or color. So of course we have different colors, that means different wavelength. Yeah, of course each one of these is, or must have a different frequency, which leads to different wavelength as well. Such a series of spectral lines is commonly referred to as emission spectrum. Why emission spectrum? Because the light has been given off. We'll see visible light on the screen. This is why we call it emission. Okay, and also remember this, when light from an atomic gas is passed through a prism or a diffraction grating, the dispersed, or you can say dispersed light appears as a series of distinct bright spectral lines. Now, so this is basically for, we can call it emission spectrum. At the same time, we have absorption spectrum. But, so how can we define emission spectrum? We can say emission spectrum, it is basically bright lines. Do you see these bright lines here? Bright lines that indicate what? We can say each one of these bright lines indicate a wavelength of radiant energy that, of course, a substance emits, radiates, or gives off, you can say, yeah? Okay, so we can say emission spectrum, these are bright lines, and of course you can say that indicates the wavelength of a radiant energy here. Now, on the same, you can say, the same time, or you can say on the contrary, we have emission spectrum. So let me just skip this one for now and talk about absorption spectrum. What is absorption spectrum? You see the difference between, for example, this is basically called emission spectrum, as you can see here, and you can see that we have the other picture here, which is right below here. Now we have, let's say, a bunch of all the colors or the spectrum, the visible spectrum here, but you can see that, you know, like right at the same wavelength of each one of these. Here, this is called emission because we have the color here, is called absorption spectrum. That is the same wavelength that is emitted here, now it is absorbed here. This is why we call it absorption spectrum. But how do they look like? These are bright lines. What about these are? Can I call them dark lines? Well then, very good. So for absorption spectrum, we can call them dark lines that indicates the wavelength of radiant energy that has been emitted or absorbed. Can I call it emitted here? No, that'll be, all right, absorbed here. But here, the first one, you can say emitted, and this is absorbed, because you can see that it is not in the let's say, in the spectrum here. So what has happened to this? And of course, you can say it has been absorbed here. Now, going back to this one, why can, by the way, so we can, of course, this one has a lot of benefits. Remember this, yeah? We can use them in spectroscopy. What is spectroscopy? To identify, or you can say device, to identify, let's say, elements in a mixture. Why? Because once we do this, you can say, because no two elements give off the same line of spectrum, which of course, spectroscopy, we can say, can distinguish materials in a mixture. Okay, so I hope that was clear. So now, if we have a bunch of, let's say, material, all, let's say, mixed together, we can use spectroscopy to identify the materials in each here, okay? And the reason why, because no two elements give off the same line, let's say, spectrum. This is why we can distinguish using spectroscopy. Okay, now what about the absorption spectrum here? Okay, so if we ask what is the absorption spectrum, now I hope we have an idea between the emission spectrum, that is when we see the color, let's say the line, the bright lines, and we have absorption, let's say, spectrum, when we don't see the lines, or you see black lines where a certain wavelength has been absorbed by, let's say, the gas or the material. So once again, what is the absorption spectrum? We can say an element absorbs light. Don't forget, okay? At a specific wavelength. So when a specific wavelength of light is absorbed here, of course, we have different colors of light here, each one of them with a different frequency and wavelength here. But when a certain wavelength is absorbed, then of course, we'll see a dark line here. So each one of these dark lines, you can say, it indicates a specific wavelength, creating an absorption spectrum, or you can say an absorption spectrum will be absorbed. And how do we will be absorbed? That means we will see them on the screen, as you can see right here. But how do we see them? By passing the light through a vapor of that element here. Okay, so let's say we have the vapor of an element. Okay, when we have a light, let's say when we pass or allow the light to pass through the vapor of that element, and then of course the light will pass through, correct? Once it pass through, if we could, for example, examine that light, let's say using diffraction grating, or let's say using, let's say slits and let's say prisms and all that, we will see, for example, the, let's say these lines right here, and of course we'll see that some of the wavelength will be missing. But how do they look like? They look like dark lines on the screen, so we can call this one absorption spectrum. By the way, we'll use absorption spectrum for a lot of uses, which we're going to talk about them. But one more time, make a difference between emission spectrum, when we see the light, and of course, or you can say the lines of light, and then we have absorption where we see dark line. That means these wavelengths have been absorbed. Now, a few more questions here. Says, how does an absorption spectrum appear, guys? We said that it appears as dark lines over a continuous spectrum. So we have the continuous, let's say, spectrum. That'll be the bright colors or all the colors that we have. But then once a wavelength is absorbed, of course, we'll see them as a dark line. Each dark line, of course, corresponds to a specific wavelength, or you can say this specific wavelength, of course, it indicates a specific material, you can say. Okay, how does the absorption spectrum compare to the emission spectrum? We say that each line in the absorption spectrum, of course, matches the line in the emission spectrum here. So you can see here, one line here, it matches one line in the absorption spectrum. Or you can say one line in the absorption spectrum, it kind of like matches one line in the emission spectrum here. So, of course, using this two here, it can help us identify a lot of materials here. Okay, so we will say, and of course, however, more, by the way, there's one more thing you need to know, by the way, okay? And we can say, because when we have emission spectrum, we normally get more bright lines compared to the emission spectrum. And that is for some reasons which we're going to study later. You can say, because if it is emission spectrum, you can say that it happens to absorption spectrum. If it is absorption spectrum, that happens at, let's say, room temperature or normal room temperature. But for the emission spectrum to happen, of course, we need high energy, or you can say some other temperature which is above the room temperature. Or let's say at higher, let's say, energy states. Or we need for the energy or the particles to be excited or have at least enough energy for this to happen. Okay, so this would be for that. Remember this, and then there is one more thing, I believe. Yes, let me not go like there is one more thing, by the way, I need to tell you here. Remember, this spectrum is basically belongs to, you can say, for hydrogen, yeah? And this one for mercury, and this one is for helium. Now, what you need to know is this. For hydrogen, there are 4 bright lines here, and you need to know or remember this one. So we can say, what are the emission spectrum, or how many lines are in the emission spectrum of hydrogen? You need to know that these are 4 lines in the emission spectrum of hydrogen, okay? Because that could be in Wrya, because they might ask you. Okay, and normally, like I was mentioning, in emission spectrum, we often get more bright lines compared to the absorption spectrum. So once again, we went through the absorption and emission spectrum. Just remember those 2, yeah? So what are the applications? What are the uses of this? Or you can say absorption spectrum. So now we're going to talk about the uses of absorption spectrum. Don't forget. So one of the, you can say one of the uses is for solar and stellar analysis, yeah? So we can use these absorption line in these, let's say, or these absorption line, or these tests, of course, to tell what are the composition, let's say, of, let's say, or to identify the materials that are, you can say, in elements and materials that are, you can say, in solar and other stellar stars, you can say, or atmosphere. That is one of the things. And of course, we can also use for astronomical analysis, and we can use this to determine what are the composition of stars as well. So one more time, what do we use absorption spectrum for? We can use them, all right, or we can use the absorption line in solar spectrum to identify elements, don't forget, that are in the solar and other stellar atmospheres, you can say. And also we can use them for astronomical uses to tell the composition of other stars, or stars in general, you can say. What about it is historical importance? Like, is it important? The answer is yes. Why? Because you can say the unique series of spectral line of each element was crucial for developing a new model, okay? As it was not explained, you can say, by Rutherford's planetary model. So the importance of that one, of course, because each one of these spectrum were unique, and of course, Rutherford or no other scientist could explain this one, so it was very important to look for a new model for the atoms, you can say, or for the atom. Now, one more question, we can say, how are elements in the atmosphere determined using absorption spectrum? This is very important, remember this. We'll say, remember this, elements are normally identified by analyzing the absorption line in, you can say, in the solar spectrum. So let's say we get these solar, let's say we get a light from the solar, that could be from the sun. Once the light passes, for example, through certain or different atmospheres, let's say, or different, let's say the atmosphere of other planets or whatever they could be, and of course, let's say, or through the atmosphere, could be even of the Earth, yeah? And then after we get the light and we allow this light to pass through, for example, diffraction grating and then prism, then of course we will get the absorption spectrum here. So once we get the absorption spectrum, we can analyze, we can see how many dark lines we have, okay? And then once we match the dark lines to the visible spectrum that we have, once we compare the two, we know that what exactly or which wavelength is, let's say, missing or absorbed here. And of course, and knowing that, we can tell, for example, what element is able to absorb this wavelength, then this is how we can tell what are the composition of each, let's say, atmosphere or whatever the material that we're testing for. So once again, elements are identified by analyzing the absorption line, that is after we use that in the solar spectrum. As sunlight passes through the solar and Earth's atmosphere, it produces distinct absorption line unique to each element, you can say. All right, one more or two more questions. That's 17 and 21. Says, how can the absorption spectrum of a gas be used to identify the gas? Well, we said earlier that by comparing the observed absorption to the known spectrum or spectra of element, yeah? So we have two. Once it passes through the gas, for example, we'll see which or what wavelength is, let's say, observed. Comparing it to the visible or to the spectrum that we have, we can tell the composition, or we can tell, for example, what gas it is. Okay, another question says, explain why all the wavelength in an element's absorption spectrum are also found in the element's emission spectrum. didn't we say, for example, why the lines match, for example, one bright line and then one dark line, that is for emission spectrum, that would be the bright line, and then we have one dark line for the absorption spectrum. Why these two match? The reason why these two match, because the wavelength in each element's absorption spectrum also found in the emission spectrum, because we can say the same electronic transition occurs. Like I've mentioned earlier, that for example, just for the sake of the example, if 10 joules is needed, for example, to go to a higher state, that would be absorbing 10 joules, okay? And then after it goes back to the same energy level, it gives out 10. So once it gives out 10, that would be the visible spectrum. Once it absorbs 10, that would be the absorption spectrum. So this is why they're the same, because during each one of these two, you can say the same transition happened. One of them is just absorbing, the other one is emitting. That is the reason why. Okay, now let's talk about Bohr's model, another model of the hydrogen atom. Yeah, remember this. In 1913, Niels Bohr, okay, he proposed a model of the hydrogen atom that explains the atomic spectrum. So far, up to this point, we can say, or up to before Niels Bohr, there were no model that could explain these spectral lines here. But then Bohr came and he explained, or he proposed a model, and of course that model could explain the spectral lines of hydrogen. But remember, later on we'll talk about this one, that Bohr himself too could not explain all the phenomena. There was a flaw with his let's say theory as well, but that'll be for later, because his theory works only for those atoms that do not have a lot of, let's say, electrons, only for those atoms with few electrons. Okay, so Bohr proposed a model of let's say, of the hydrogen atom and explained the atomic spectra, combining both classical and revolutionary principles that are not covered by classical physics, you can say. So how did Bohr's model compare to Rutherford's model? Remember this. These are, so Niels Bohr basically combined between classical and, let's say, modern physics, you can say, yeah? So what did he, or what are the things that, for example, were common to Bohr and Rutherford? Remember now, up to this point, we can still quote Rutherford as part of a classical scientist here. So what were the similarity, or how did Bohr's model compare to Rutherford's model? Even Niels Bohr said that, let's say, electrons orbit the nucleus in planetary models, yeah? So both models have electrons moving in orbit around what? Around the nucleus. However, Bohr's model specifies that only certain orbits are allowed here. So remember this, okay? Bohr said that we only have certain, let's say, certain orbits, okay? We can only have certain orbits, like it's not just random. Okay, so what is unique about the electrons orbit in Bohr's model here? Okay, so, and of course he had some specification, yeah? He didn't just say, for example, electrons orbit the nucleus and that's it, yeah? He had some specification. He said the electrons can only occupy, this is basically, you can say, that'd be for revolutionary physics here. He said electrons can only occupy specific orbits and of course jump instantly between these orbits. Okay, so we have certain orbits, electrons can only jump, for example, from one orbit to another, and electrons cannot exist between any two of these orbits. So it is either, for example, from one orbit to another, it cannot be anywhere in between these orbits. Okay, so never being found in between. How does the Bohr's model differ from classical physics regarding energy emission here? So of course, he said that, or you can say the hydrogen atom does not emit radiation while in these allowed orbits. It can only emit radiation when it goes for, let's say, when it is, going from, let's say, higher level to a lower one. That would be the emission spectral line. If it is the emission, if it is the absorption, of course, that is when an electron, for example, goes from a lower energy, let's say, level to a higher energy level, because it absorbs the energy, then goes to higher. But if it is emitting energy, that would be from a higher level going to a lower level. So you can see that the hydrogen atom does not emit radiation while in these, let's say, allowed orbits, the total energy remains constant. So as long as it is in the same, let's say, orbit, at the same energy level, it does not emit energy, so we can say the total energy remains the same here. How does the electron emit energy according to Bohr's model? Remember this, okay? So if we look here, how does electrons emit energy? Well, first of all, let's say we have an electron here, okay? So this electron gets energy. Once it gets energy, of course, it goes to a higher energy level. So we say it gets excited, yeah? So now it has a high energy. Once this electron is going down, that'll be the second part here. As it goes down, for example, because it is unstable, it doesn't stay there for too long, let's say, then it gives out this energy here, yeah? And of course, this energy that is emitted is the same energy that is absorbed, which went with to the higher state. But now it is going to emit or radiate this energy. And this energy, of course, it becomes one of the spectral lines, you can say. So he said that energy is emitted only when the electrons jump from a higher energy level to a lower energy one. So what happens when an electron jumps from a lower energy to higher? Of course, that is the absorption of the energy. So in that case, energy is not emitted. You can say energy is absorbed. But if it goes down from a higher energy level to a lower one, then that is the only case where electrons emit or radiate energy. So how do we find the energy, or how much energy is radiated? And of course, we can use this equation here. It says the energy of the emitted photon equals to the energy decrease of the atom. And how do we do that? We'll say energy of, or you can say initial energy state. So we have different states, yeah? We've learned that before, that energy is equal to HF, correct? But now this one here, if it is going to emit energy, we can say that is going to be the difference between two energy levels. Remember, that is for emission of the energy, yeah? So if that is the case, we have an energy called this, for example, A. That is basically the initial, you can say, level. As it go down to this level here, that is going to be the final level, you can say here. And of course, we'll say initial minus final. That would give you a difference in energy. That difference in energy here, it gives you this photon here, or the energy of this photon here. So you can also see we have absorption and emission here. What happens at the absorption? We have an electron, let's say, at an energy level, let's say. It could be at the ground state, let's say. And once, for example, energy comes and let's say it's absorbed by this electron here. Of course, now this electron, it jumps to a higher energy level. You might wonder, but which energy level exactly? That depends on how much energy is in this photon here. If this energy, for example, that this electron gets, for example, if it is equal to this difference, it will jump to this level. If it is big enough, it can, for example, that equals to the difference between these two levels, it will jump to this one. If it is bigger than that, if it is enough, for example, to jump to this one, of course, it goes there, and then it goes there. But remember this, guys. This let's say, jump, it is not random. It has to be very specific. So if the energy that you have, for example, if it is given, let's say, let's just use some random numbers. Let's say the difference between these two energy levels, let's just say it is 2 electron volt. Let's just say, yeah? If this energy that is coming, if it is 2.5 here, all right, then let's say this is 3 electron volt, yeah? 3 electron volt here. Now, if that is the case here, you might say, it's not like this one here. So this is 2.5, don't forget. And of course, this is 2. That's the difference between these two, and the difference between this 3 is 3. This 2 is 3. So we have 2 different, let's say, energy states. And now remember this, because 2.5, it is bigger than 2, yeah? So we cannot say it will jump to this one. There is 2 basically, and there will be 0.5 electron volt extra. No, it doesn't happen. We cannot say that, for example, it goes to this one 3 here, because clearly that is not as big as 3 here. All right? So, but when will it jump? It will only jump if, for example, the difference between one of these energy level, for example, just remember this. If the difference between these two energy level, if it was 2.5 electron volt, then this photon will be taken, of course, then this electron will be able to jump to this point right here. Okay? If it is less, it cannot. If it is more, it cannot. It has to be only the same amount of energy so that the electron can take this energy and then jump to that energy level. Because remember, electron cannot go somewhere half in between the two levels. It has to be only or exactly this level. And how will it be exactly this level? That is only if the amount of energy that is received, it is equal to the difference between this and any other these energy level. If it is the same amount, it can jump to the difference between these. If it is not equal to, then of course it cannot do the jump, so it will stay as it is here. So this, once the energy is absorbed, that is called absorption. You can see the electron jumps to a higher energy level, but there it will not be stable. It will not stay as or like that forever. That is basically the state of, or you can call it excited electron here. Then after some time, this excited electron will go back to the same energy level. You can say, now emitting the energy that it has, for example, it has now. So if it goes from higher energy level to lower energy level, then it has extra energy, so it has to get rid of that energy. And that energy, of course, will be given away as electromagnetic wave, or you can say a photon in that case. And of course, if it is in a visible or in the range of visible light, you can even see that light. Okay, so this is basically what happens for this one here. So you can see that when a photon is absorbed by an atom, an electron jumps, let's say, to a higher energy level. But when an electron falls back to a lower energy level, the amount of energy or the amount the atom releases a photon here. That is, you can say, the energy, yeah? Especially, that would be visible light, of course, if it falls into the category of electro or visible light. Now, let's talk about Bohr's model, all right, of the hydrogen atom. So what is exactly Bohr's model? What was Bohr's model for the hydrogen? We said that for hydrogen, remember these points, yeah? Let's say ground state and Bohr's radius. Yeah? What do we call the ground state or the lowest state of energy for the hydrogen atom? We can say that the lowest energy state, right, with the smallest radius, it is called the ground state. What about the radius of that atom? The radius of that atom, you can call it Bohr's radius. Okay, and then at ordinary temperature, watch this. At normal temperature, we can say most of the electrons exist where? Exist at the ground state here. Remember this because you will need this one for later on. Okay, so once again, at ordinary temperature, most of the electrons are in the ground state, which is very close to the nucleus. We know that the closer the nucleus, or the closer the atoms to the nucleus, the more bound the electrons are. That means there is a strong, or you can say there is an electrostatic force between the nucleus and the electron, of course, which bounds, kind of like locks, or you can say electrons in place, yeah? Or basically that force dominates the electron to keep them around the nucleus or not to allow them to be free here. Okay, so but the further the electrons are from the nucleus, the less that force, or the less the nucleus has control on them, so they are more free, and of course they can, or they are able to conduct, let's say, electricity if they are free, or can of course add or contribute to the chemical property of that element here. All right, two more thing here. Now, what about photon absorption in excited state? Remember this, light with energy matching, the difference between these two energy levels can be absorbed by the atom. We've mentioned before here, if a photon came, for example, and if the energy of that photon it is equal to the difference between any of these two energy states, the ground to one of these states, then that photon of light can be absorbed, then the electron will jump to a higher state. If not, then of course it will not be taken. Then once at a higher state, of course, it will emit, or you can say go back to the same energy level and then emit that energy here. So that energy, of course, you can call it spontaneous emission. But before that, going back to this, we said if it is equal to the difference, it will be taken. If not, it will be not taken. Once it is taken, then the electron can jump into a higher state of energy, and that's it. And then, of course, we can call it excited state, moving into orbit further from the nucleus. Observed photons create a dark line. We've mentioned that one. That is once they absorb the light or the photon. Then for the spontaneous emission here, an excited electron may return to a lower energy level, emitting, of course, the photon that they have observed here along the process. Now they will emit, yeah? Then the emission, let's say radiation of electromagnetic wave, you can say it creates a bright line in the emission spectrum. Okay, that is if considering that this photon was equal to, let's say, or in the range of visible light. Energy and spectral line here, don't forget there's one more thing here. The energy of the emitted photon depends on the size of the electron's jump. So we can say the bigger the jump, the more the energy is absorbed. And of course the same thing, the bigger the energy released or emitted when it goes down or to the ground state here. Okay, and then larger jumps, more energy, and of course in different spectral line. Each jump between any two waves or any two levels, of course, it gives out a different spectral line, different color, you can say. Yeah? Bohr's model was successful in explaining those spectral lines of hydrogen. Yeah? Okay, so of course, this would be, you can say, the colors of light. These are red. You can say this is light blue, I don't know, sky blue, whatever. And of course, these are kind of like more into, you can say, violet here. Okay, even though the colors are not very different here, or maybe they didn't emphasize on the difference on those colors as well. But remember, we have 4 spectral lines, 4 bright lines for hydrogen atom. The last two thing here, that would be absorption versus emission spectra. Absorption when, for example, when we have the light, for example, if a photon is absorbed, okay, then of course we get a dark line. If it is emission, we get a, let's say, a bright line here. This will be the difference between the two. For next time, we'll talk about the northern lights. Of course, you've seen the, for example, those beautiful colors that happens at the northern, for example, let's say, or the poles, let's say. We'll talk about what are the reasons for that and why does this happen, but that is all for next time. Till then, keep practicing and I'll see you soon. Assalamu alaikum wa rahmatullah.